Assalamualaikum and hi to everyone. My name is Nur Aisha binti Juso. My metric number DF230029. Today I want to explain the background of the project. Concrete beams are key component in structure designed to safely carry load in building and brick. Traditionally, beams are often over-designed using more material than necessary. This not only increase cost but also has a great environment impact. To avoid mathematical methods such as log-large multiply can be applied to find dimensions that are both efficient and strong enough. Okay, I can continue the explanation for problem statement for this project. First, traditional method may over-design beam. Second, need balance between safety and material efficiency. Next, construct string dimension must be maintained. And the last for the problem statement is Lagrange method provide a way to minimize while honoring those conditions. Okay, for the objective, the main goal of this project are to minimize the cross-section area of the beam, to safely carry a bending moment of at least 1.5 kN and to keep the total area below 0.5 meter square. This approach aims to produce a cost-effective, efficient and structurally reliable design.
My name is Nur Shawani Fatia binti Abdul Aziz. My metric card number DF230027. So I can continue. My part is literature review. So for the this part, reinforce concrete, combine concrete and steel to resist apply force more effectively. So why plain concrete is strong in compression? It is weak in tension. The embedded steel takes up tensile and shear stress, making the structure strong and more durable over long span. So one major advantage is it a long service life for structure like bridge and tunnels, especially in harsh environments. Durability based design focus on limiting damage from combination or chloride penetration. However, understanding how this factor in trade is complete. So, research by Ha Wong Song show that combined effects like carbonation and chloride added together can speed up deterioration and reduce lifespan. So, for this project, I began by exploring several potential topics and selected one that is relevant and practical within the field. After that, I defined the main problem, explain it, is inefficient, and outline clear to objective guide the study. So, to support the project, I conducted a background study and literature review by referring for the case study. So, based on the understand gain, I selected an appropriate method and applied it to solve the identified problem. The results from the calculation were then analyzed and discussed in relation to the project objective. In conclusion, the project successfully met its goal and offering meaningful insight with suggestion for future improvement. Continue my part for methodology. The main formula used in this project is the bending equation, like M equals 0.17 times B times H square. This formula relates the moment capacity to the beam's width and height. We apply the Lagrange multiply method to find the optimal dimension of the beam. So there were two key constraints. For the first, the bending moment must be at least 1.5 kN meters. And second, the cross-sectional area, which is B times H, must not exceed 0.5 square meter. Then, using this condition, we carry out calculation to minimize the beam's dimension while making sure that all structure and safety requirements are met.
Step 1. Defining the problem. The goal is to minimize the cost function CBH equal to 2B plus 3H. While satisfying equality constraint, the cross-sectional area must be BH equal to 0.5 meter square. The inequality constraint strength requirement is 1 per 6 BH squared must be over or equal to 0.006 meter cubic. The practical limit is B is over or equal to 0.2 meter, H is over or equal to 0.3 meter. The Lagrange method handles the equality constraint BH equal to 0.5 explicitly, while inequality constraints are verified later. The Lagrangian incorporate the equality constraint L B length BH lambda equal to 2B plus 3H plus lambda BH minus 0.5. Partial derivatives are computed as follows. Derivative B, the term 2B is 2 lambda multiple BH yields lambda H. The result is 2 plus lambda H. Derivative of H, the term 3H is 3 lambda multiple BH yields lambda B. Result in 3 plus lambda B. Derivative lambda BH result in BH minus 0.5. By setting the derivative to 0, locate the critical point where the cost gradient aligns with the constraint gradient. This gives 2 plus lambda H equal to 0, 3 plus lambda B equal to 0, BH equal to 0.5. Solving this equation identifies candidate point for optimization.
So my name is Muhammad Shazwan. My check number is BF230001. So I want to continue about the result for this problem. So for the 4 is solve the system of equation. So from the equation 1 and equation 2 we combine is we get 1.5 H is mean height. So substitute B into equation 3. Yeah? So B is mean 1.5 height, and we get the answer is 0.866 meter. So check the inequality content. So for the strength is we get 0.5 and what is 0.866 meter. It means more than greater than 0.2. So for the height is 0.577 meter, greater than 0.3. So we compute the minimum cost, which means we get 3. So the final design is white. For the base is 0.866 meter and height is 0.577 meter, and for the cost is 3.483 per unit. So 3.463 units. So for the verification, cross section area is 0.866 multiplied is 0.577. We get 0.5 meter square. For the strength is we get 0.048 meter square, greater than 0.006 meter square. So for the cost is minimum value under all contained.
Hi, my name is Wan Muhammad Nyawa Saiful Haq and my metric number is DF230021. Today I will talk about discussion and conclusion. For the first is discussion. The Lagrange multiply method successfully designed a cost-efficient and strong beam with minimizing material while safely resisting bending. The dimension we found to about 0.9 meter in height and 0.56 meter in width, which efficiently use material without exceeding the 0.5 meter square area limit. However, this simplified approach focuses mainly on bending and does not account for shear, dispersion, or durability, which may need to be considered in future design. For the conclusion, in this project, the Lagrange multiply method successfully optimized the dimension of the beam. The final dimension of about 0.9 meter in height and 0.56 meter in width minimize material while safely resisting a bending moment of 1.5 kilonewton per meter and staying within the area limit of 0.5 meter square. This shows that mathematically optimization can help engineer design structure more efficiently. The method can also be applied to more complex design in future projects.